all the messages that I want to get across. So I think now I will leave the word to Ralph Dorn to introduce our awardee, the person who has won the Junior Excellence Award. So Ralph, please, the word is yours.
Yeah. Thank you very much, Jean-Charles, for the announcement and for the introduction. And I welcome you all to this very honorable session. It's always a pleasure to present awards. And the EFC Excellence Award is one of the main tasks that we set ourselves for the EFCE Working Party, apart from industrial surveys, teaching surveys, webinars. We have the Excellence Award, and now we have it for a couple of times, and it's highly regarded. It's for the best PhD thesis in thermodynamics and transport properties within a 2-year period. So this is something. Now, usually people are quite nervous in these, and it's a little bit stiff if you give away an award. So therefore, I would like to tell you some stories first about our previous winners of this award. And this is quite interesting. It was first given 2009 to Irene Karakatsani. So she made a very good career in industry afterwards. She is now representing Denmark in our EFCE Working Party. And actually, she is now a member of this committee who today found who's now announcing the winner of this year. So this is Irene, 2009. 2011, it was Maria Francisca Casale from Santiago. The winner, Maria, later became, after postdoc in Berkeley and Eindhoven, she joined Bayer, so she became a colleague of mine. And a funny story, at the ESAT, she got to know Joseph Fonseca, who is the Helmut Knapp Award winner, and who also became a co-worker in my group, and they are married and have 2 children. So this is about stories. Now, the winner of 2013, the stories go on. Now, I'm not talking about private matters. The winner is Christoph Held. And Christoph Held is very well known in our community. He is chairing a session here at the ESAT. And if you have Christoph Held in the auditorium and you're the chairman, you can be sure that you are going to have a very good discussion with very good questions. 2015, it was Björn Maribo Mogensen. Now, he also is very active at this ESAT. He founded his own company, and he's very active in our community. Then 2017, we are getting closer now. It was Owen Willemsen. He is here in the auditorium. He became also representative of Norway in our working party, very active, and he is the PhD advisor of the winner of today. So this is really quite unusual. Then the last winner before was Monia Martins from Aveiro, and she's also very active in her research and doing many publications. So now I have to say for this award, we always need a good sponsor. So I know this is always difficult to find a sponsor. Bayer was a sponsor twice. And for this year, we found a generous sponsor, and it was ProSim. So we are very thankful for the donation of the money and the expenses that we have coming with this. Now, the committee is always selected by the EFC Working Party. And I give you the name of the committee. It's Anna Soto, who is at the ESAT, Irene Karakatsani, myself, and virtually not here are Jadran Wabetz, he was the chair, and Professor Kurt Peters. I have to tell you, we had very good candidates this year, so excellent candidates. The main criteria that are considered is the breadth and the depth of the thesis, technical quality, scientific impact, including industrial relevance, innovation, and dissemination of the work. So now our winner of this year's, now this is not like the Oscars where you don't know where it is, you already know it, it has been published, and he's on the stage with me. It's Ailo Aasen. He applied his Master of Science in Applied Physics and Mathematics from the Department of Mathematical Sciences, is NTNU in Norway. And at the Department of Energy and Process Engineering, he made his PhD under the supervision of, as I mentioned, Øyvind Wilhelmsen. And currently he holds the position of research scientist and software developer for computational thermodynamics and fluid mechanics at SINTEF Energy Research. His PhD thesis, for whom he got the award, deals with 3 of the most challenging topics in the field of thermodynamics. You know, all these dangers happening at the same time, like in the movies. The development of an accurate equation of state, the thermodynamic description of quantum fluids at low temperatures, very important, and interfacial phenomena applied to nucleation. Just let me mention a little bit about why we selected him. The technical quality of the work is outstanding, and he had a paper even published in Physical Review Letters. Another paper was picked as editor's pick of the Journal of Chemical Physics. He had 16 papers, of which 13 are in highly recognized journals, and he has been cited more than 150 times. And the jury was particularly convinced of his very innovative approach to include quantum effects into classical Helmholtz energy equation of state. His theoretical work has been implanted already in some process simulators. So please, Ailo, we are all very curious about your presentation, and please start.
Thank you, Ralph. And of course, I'm honored to receive this prize. Thank you to the committee and to ProSim, of course, the sponsor. Take control here. Get a laser. So today's topic is cubic equations of state for quantum fluid mixtures. I'm Ailo Aasen. This has been a work done together with my co-supervisor, Morten Hammer, and also my main supervisor, Øyvind Wilhelmsen, and Joan Noel and Sylvia. So what are quantum fluids? Well, it's these 4 fluids shown here in this table: hydrogen, helium, neon, and deuterium. Also, of course, other isotopes are possible. They're among the most abundant elements in the universe. Hydrogen and helium are the most abundant by mass. And they have vapor-liquid equilibrium at extremely low temperatures. Here you see the critical temperature, 33.2 Kelvin for hydrogen, and all of them are below 50 Kelvin. They have striking features such as inversion of heat capacities. For example, along the boiling point curve, you have the heat capacity of the liquid is less than the heat capacity of vapor for normal hydrogen. And you have barotropic inversion for certain mixtures, where a liquid can float on top of the vapor. It's highly unusual, of course. And the reason we are looking at these fluids is that hydrogen is currently being evaluated as a sustainable energy carrier. And in particular, to transport hydrogen, it is being evaluated whether liquid hydrogen is a good way to do it, in the same way as liquid natural gas is a convenient way to transport natural gas due to the reduced volume. And the problem here is there are significant quantum effects in the VLE region, because otherwise these molecules are simple, non-associating, non-polar, and essentially monomers. They have significant quantum effects. And one way to see that is that the thermal wavelength is comparable to typical intermolecular separations. So here we have the definition of the thermal wavelength. And I want to point out that it increases when you go lower in temperature, and also when the mass of the molecule is low. That is why these molecules are so affected by quantum effects. So a recap of cubic equations of state. You know, there are modifications of van der Waals equation of state published 150 years ago. In the right box here, I show maybe the most well-used equation of state, most used equation of state of the cubic type, namely the Peng-Robinson. You have this repulsive part, RT over V minus B, and you have an attractive part. And I've circled here the two key parameters in the cubic equation of state, this attractive energy parameter, A, and the repulsive co-volume parameter, B. And this co-volume is essentially the volume of the molecule, so a size parameter. Pure components, you model A as a correlation in temperature, usually fitted to the saturation curve, and B is a constant. So the advantages of cubic equations of state, the reasons why they are so widespread today, is that they are simple and robust, as you can see of its form, is low computational costs. You usually correlate them so that you have the exact critical temperature and pressure. It's been shown to correlate VLE well for many mixtures, especially in the hydrocarbon industry, and it is familiar to industry. Oops. However, they exhibit poor accuracy for quantum fluids. So let me elaborate on that. So let's look at the performance of the Peng-Robinson equation of state for quantum fluids. So on the left here, I show pure hydrogen. And in this paper by Legwenick et al. From 2016, they did extensive work trying to fit this Peng-Robinson equation of state for these quantum fluids. But their formulations have huge deviations in certain thermophysical properties. For example, the liquid heat capacity at saturation. And also I show here the alpha function, so this attractive parameter function for hydrogen. So experts of cubic equations of state know that this should be a decreasing function of temperature as the dashed orange curve. But when you try to fit it to saturation data, you get this non-monotonic behavior approaching zero when you get close to low temperatures. And this has been hypothesized to have something to do with huge deviations in heat capacity, since the heat capacities involve derivatives of the alpha function. On the right, I show the helium-neon mixture, which is actually the motivating example for us at SINTEF and why we got into this. 2018, we looked at the hydrogen liquefaction process using helium-neon as a working fluid. And here you see the binary phase diagram plotted at different temperatures, where the dots are the experimental results. And you can see there is a rather poor match. And in particular, you see that, for example, for the yellow curve, the experimental data seem to close the envelope, whereas the equation of state, the Peng-Robinson, does not. And I want to emphasize, we tried a lot of different equations of state, probably 10 of the soft type and so on. Excess gives mixing rule, but none of them were able to model it. And that actually motivated my PhD work, trying to fix this issue. So now let's take one step back and look at a molecular model of quantum effects. So just simply blind fitting of this cubic equation of state did not yield any improvement. So let's go back to what the molecules are doing. And for that purpose, we will need a molecular model for classical fluids first. And as already mentioned several times in this conference, the Me potentials yield a decent description of many nonpolar monomers. They're essentially generalized Lennard-Jones potential, and you see that they have a versatile shape by varying this repulsive exponent. We are interested in quantum fluids, and to get a model for that, we get some help from Richard Feynman, shown in the picture on the right here. So in his book in 1965, he looked at a perturbation expansion to account for quantum effects. And it turns out that you can still use the machinery of classical statistical mechanics but not with a pair potential, but with an effective pair potential. That you see here, the Me Feynman Gibbs potential equals the Me potential at high temperatures and is corrected with this Laplacian term scaled with the square of the thermal wavelength. And the square of the thermal wavelength is proportional to 1 over T. So it is a semi-classical potential because it depends on the temperature. However, the nice thing here is that the molecules can still be considered localized, which is important if you want to do classical statistical mechanics. And I want to emphasize very strongly, there are no new tunable parameters. If you have a good potential in the classical regime that is at high temperatures, then the quantum corrections are given without any new fitting. So in my PhD thesis, we did this exercise. We determined the optimal force field parameters for the Me potential by combining experimental data with molecular simulation of these Feynman-Gibbs corrected Me potentials. And of course, fitting data to molecular simulation is very time consuming. So we also did a lot of work on developing a thermodynamic perturbation theory. It's called SoftVRQ Me and is an extension of the SoftVR Me framework. You can also mention this has previously been done for square well fluids, Feynman-Gibbs corrected square well fluids by the group of Alejandro Gil Villegas. Here you see the optimal parameters for the Feynman-Gibbs corrected Me fluid. And as you can see, there are no more parameters than those originally in the Me fluid. And we didn't fit this attractive exponent. We kept it at the London dispersion value of 6. And this development of the quantum corrected potential is detailed in these papers shown here. So I want also to give you some takeaways from what we found out with these quantum corrections. Because these quantum corrections actually affect all substances at low temperatures, even if you're not interested in the 4 quantum fluids I'm mainly discussing here. So you will find that there are essentially 4 qualitative features. First of all, it's a harder repulsion. So this repulsive part, the positive part of the potential, becomes steeper. There's a lower well depth. So this effective epsilon becomes a smaller value as you go down in temperature. It is more long-ranged, which is seen in the inset here. The red quantum corrected potential is lower or has a higher magnitude than the classical limit at high temperatures, which is shown in black. And crucially, which is a crucial effect, you have quantum swelling, which is that the effective sigma, so the effective diameter of the molecule, becomes larger as you go down in temperature. And as you know, the size of a molecule crucially impacts the structural properties of the system and is important to account for. I also want to mention that several of these features actually make perturbation theory converge faster, as experts in perturbation theory will know, such as longer range and harder repulsion. So let us now try to incorporate this molecular insight into a cubic equation of states. And here is the key step. So based on these optimized quantum corrected Me potentials, we derived quantum corrections to the co-volume in the cubic equation of states. And we didn't do any further fitting. What we did was that we introduced this beta parameter, which scales the classical co-volume, and it is given by this expression here in the middle, a cubic power. And you will notice that it is 1 at the critical temperature because you scale it with the effective sigma at the critical temperature, so that the value of the quantum corrected co-volume is the same at the critical point. And this is actually important to retain the nice feature of cubic EOS, that they are exact at predicting the critical temperature and pressure. So I'll just give some details to the people interested in cubic equations of states. We did a simple linear mixing of the co-volumes for mixtures. The alpha function was the true formalism, which has become accepted and preferred in the later years for cubic equations of state. Used the quadratic mixing of the attractive energy, and we used a volume shift. So there are 4 pure component parameters and 1 binary interaction parameter. Now let's go to the results. Here you see the quantum Penn-Robinson for pure hydrogen. Solid curves are the predictions from our equations of state, and the dashed curves is the reference equation by Leachman et al. And on the 2 upper plots to the left, you see an excellent match on the vapor-liquid equilibrium curves, both on the temperature density plot and the temperature pressure plot. And as you can see, the critical temperature and pressure is exact. The remaining plots are supercritical isobars, so supercritical densities in the 3rd plot on the top. And on the bottom here, you have the residual enthalpy, the speed of sound, and isochoric heat capacity. And I mean, the takeaway is that it works rather well. And now let us go back to the motivating mixture for us at Sintef Energy Research. And here you can see the crosses, the experimental points actually coincide pretty well with the predictions of the equation of state given by the curves. And of course, the qualitative features are correct. The envelopes close when the experimental measurements indicate a closing envelope. I'll also show the hydrogen-neon mixture, which exhibits an interesting phase diagram with liquid-liquid splits at low temperatures and high pressures, and a VLLE curve. And you see that the agreement is rather good. And finally, I'll just show the helium-hydrogen mixture, as this is the mixture which has the strongest quantum effects. Helium and hydrogen are the strongest quantum fluids. And you can see it's a rather good match. At 1 temperature, there seems to be room for improvement, even though there is a bit scatter in the data. But overall, it's very good. I also want to quickly mention this open source implementation we have here at Sintef. So you can develop, you can make this possible for yourself. If you want to do predictions for a ternary mixture, for example, you need a script of the length shown on the left. That out if you're interested in quantum fluids. Some conclusions. Rigorous quantum corrections were incorporated into the cubic equation of state with no new fitting parameters. Quantum cubic equation of state retains all the advantages of conventional cubic equations of state. They yield an accurate and simple model for mixtures of quantum fluids. And I'll also mention that we tested both Penn-Robinson and SRK, and quantum corrections in the Penn-Robinson equation of state was the most accurate. And with that, I want to thank you for your attention.